Another important concept to consider is the forward rate. This determines the dynamics of the system. If the system has a steady state, it will reach the steady state eventually, but the question is how fast it reaches the steady state. Really fast or slow. This time scale is determined by the forward rate. And the forward rate, for example, is per concentration, per unit time, some amount of reaction will happen. So this is a basic idea. Let's say 10 to the power 7, just to give you an idea. And let's examine the unit on the left-hand side versus the right-hand side. You can see a concentration and time. The scale of time is not given yet. But here you see concentration squared. And because Kd is concentration, here we have concentration squared on off rate as well. If you put this example, you can see that concentration will be cancelled out. So concentration squared becomes concentration. And you're dividing by time. And this f becomes some number, which is 10 to the power 7, which is what we have chosen for an example. Now what you can do is to divide both sides by 10 to the power 7, which means that we'll have time on the right hand side. On the left hand side, we have to divide by 10 to the power 7. What does it mean? Well, it scales the time by 10 to the power 7. What used to be 1 second now becomes 10 to the power 7 times faster. So it essentially scales the time. It makes the time run faster. So if you have a higher forward rate, then the reaction will happen in a shorter amount of time for the same amount of reactant produced. So in that sense, you can interpret f to scale time. So you can make time run faster or slower. So eventually, what it tells you is that if f had a larger number, it means that f is fast, then reaction will happen in a much shorter time scale. So the reaction will happen in a much shorter time. So all of those means that if you know the forward rate and the reverse rate, we can predict the dynamics completely. Knowing f and r is equivalent to knowing f and kd, because kd is r of f. Those two are all we need to know. And you can have this imaginary simulation of LPS available at many different concentrations at many different durations. It can be totally arbitrary. You can calculate. If LPS is same as KD, as we have learned, it will reach the half maximal concentration of TLR, total TLR, if the time given is enough. In fact, if LPS at the concentration of KD is given for long enough time, it will reach that value. And then after LPS is gone, after enough time, it will actually reach down to 0. But then if you give 2 times the concentration of KD, it doesn't saturate all the way to total TLR concentration, because as you can see in this graph, if 2 times KD is given, it still doesn't reach the maximal concentration. So here you go. But the time course of when it reaches is the same, because F remains the same. So you reach that value, steady state value, after enough time. And of course, if the time is not enough, it will not, before it reaches the steady state, it will stop and drop down again. So you can do this on your computer, and you can put in all sort of different concentrations over time of LPS over time, and you can see just how much of TLR will become active. So we are moving on to week 5. We have already spent so much time. I'll make it as brief as possible. But before that, I should tell you something. This is called a pedagogical lie. Mathematics is a rigorous discipline, and telling you the concept of mathematics requires you to give you some false ideas, which is not rigorous. So basically what I have to do is tell you a bunch of lies and give you a lot of concept. And over time, I gradually decrease those lies and become more precise. This is really just a way of teaching. So when I give you those lectures, try to capture the main idea. Details, it should be fine-tuned later stage of the lecture or later stage of your learning. So eventually you will get to this complex dynamics of LPS and TLR. The actual TLR that binds to LPS is called TLR4, and the intermediate process between the NF-kappa B activation and the TLR LPS binding is a complicated pathway. We don't really talk about that. You will get there in your later stage of learning. What we have discussed is the binding of LPS on TLR and it will activate TLR. This simple dynamics itself is also simplified. Our previous simplification has been possible under the assumption that LPS is actually close or larger than KD. If KD is so low, which is true, which is because KD is about nanomolar, then because there are overwhelming amount of LPS and TLR complex will stay stably and they'll exist for a long time, so TLR will be active. So this dynamics just naturally happens. One thing we have to realize is that in reality, the problem is LPS binding with inactive TLR doesn't always make an active TLR because there's a reverse rate. It comes back. Yet we suppose that F is much higher because KD is nanomolar. So predominantly everything will go this way. This is the reality of what happens. It is actually true that LPS and inactive TLR bind each other and dissociate freely. But once LPS is bound to TLR, it makes TLR active. And after that, LPS will dissociate freely. So the actual reaction that happens is LPS and inactive TLR binds, and that with some probability leads to this complex, bound complex. And when it's bound, it almost always goes to active TRL. This part is important. This is known as enzyme kinetics, and it has been mathematically described by Michaelis and Menten. The first part of this reaction has been described in the previous lecture. I have written down every single step of how to get to the LPS negative TRL complex, and we treated LPS negative TRL as active TRL. But the fact of the matter is, it actually has to be converted into active TRL, and LPS become free again. There's one major assumption here, because this tells you that the reaction happens in only one way. When it is bound, it has to make the TRL active. And this process is called the quasi-equilibrium, because if you are thinking about equilibrium, there should be some reverse rate, but we're not thinking about that. But this is quasi-equilibrium. It mostly makes sense because reaction is mostly forward. This is irreversible process. Then this latter part of reaction can be described the same way. The amount of active TRL, the rate of change of active TRL, which is d active TRL over dt, is just the rate multiplied by this complex, LPS negative TRL complex, just like that. And in the previous week's discussion, we learned that LPS TRL complex can be written this way. And we just simply plug it in. When we noticed that in the previous discussion, the maximum concentration is reached is the total TRL. And if you think about converting it into rate, and there's the rate constant, so K multiplied by TRL, total TRL, will be the maximum rate that it will reach. The maximum rate, let's write Vmax. And the whole thing can be written like that. This is the Michaelis-Menten equation.